Hey guys, in the last video we estimated what our drag would be in order to find a more accurate cruise speed. Also, I just want to go ahead and mention from the last video, I found that our cruise speed was like 15 meters per second, and we found that our stall speed was, 5 meters per second. So we're about 3 times our stall speed. So we're actually in a pretty good, um, which is actually good. You don't want to have your cruise speed be under your stall speed, otherwise you're going to stall. I just want to kind of mention that real quickly. Um, but now what we're going to do is we're going to um, take what we did in our SolidWorks. We're going to apply it to, um, well, we're going to apply it to XFLR. So it's really important to be in millimeters grams second for this part because you're going to be able to get accurate values for moments of inertia, which are going to come into play in a little bit. So I would recommend, um, if you have your sizing thing, maybe making either a new sheet or just I'm going to throw it in wing size. Why not? We already updated our estimated weight, which is good. And then now what we need to do is we need to find what are called our moments of inertia. So if we look in XFLR5, I'm just going to open up this. As you can see, if I edit the analysis and I go under mass and inertia, I can opt to use the plane inertia, or I can specify my own inertias, right? So that's for dynamic. For static, I went ahead and renamed these, by the way. Just want to go ahead and mention that. So the way that I've defined my XFLR5 simulation is that the CG is at the origin in XFLR5. So the wing is placed relative to the CG. So as you can see, the leading edge is in front of the CG. So what I can do is in my analysis definition for static, I can go ahead and just specify, I can just uncheck use plane inertia and specify my own plane mass and CG. I can actually go ahead and change that to 394 grams, 0.394, and hit save, and hit OK. And then now, I can run the sim, and it'll run all nice and fine. And then now, for dynamic, I'm going to do a similar thing, where under mass and inertia, I'm going to uncheck use plane inertia, 0.394. CG should also be 0. And then we need to find IXX, IYY, IZZ, and IXZ. So, in SolidWorks, as you can see, we're actually kind of lucky because IX is in this direction, IY is in this direction, and IZ is in this direction. And those are the same 3 axes as in SolidWorks. As in XFLR5. X is in that direction, Y is in this direction, and Z is in that direction. So we can just straight up take these moments of inertia from XFLR, throw them into SolidWorks. So as you can see, IXX is right here, and this is in grams per square millimeters. So what I'm going to do, I'm going to take that value, and I'm going to say, I'm going to call this IXX, and then I'm going to look up grams millimeters squared kilograms meters. And then, as you can see, 1 gram square millimeter is 1.0 e to the 9, so 10 to the negative 9 kilograms square meters. So we can just take this, multiply it by 10 to the power negative 9. Oh, and then I should probably put an equal sign in front of this. And then, here we go, kilogram meter squared. And then we'll do that for this, and 4. So found I x x. Now we need to find I y y. So we'll repeat the exact same process. Um, and then I'm going to do the unit conversions later. But yeah, essentially you'll find those values, convert them here, and then because the unit right here is given as kilogram meter per second, you put that in there. Then what we're going to do is we're going to go and we're going to do what we did last time. I'm just going to save this for now. I'm going to assume, because those were all my previous values. What we need to do is we need to find um, the induced angles. So I don't know if you guys remember this or not, but um, under wing placement, um, so this is going to stay the same, this is going to stay the same, this is going to stay the same, sorry, this is going to stay the same. This will change, and then that will cause some of these other values to change, as well as this. Stall speed B3, B4, and B6. B3, that's going to change. B4 should be fine. B6 will also change. Let me make this a function of this. There we go. So then, here we go to wing placement. It changed. Okay, beautiful. And then wing sizing B5, which is wing area. And so now, for wing placement purposes, um, we are going to recalculate um, this value here, and that will change our wing placement as well as our wing incidence. As you can see right now, it's like 2.88 degrees. So let's go ahead and find out what that value is. Go ahead and run this analysis. Beautiful. And then let's grab negative 18, this be 5.63. Then we'll choose negative 15, 4.75. And that should be divided by 3. And now that value was lowered. So as you can see, um, wing incidence is constant, and now also our placement relative to the leading edge has changed. So we can go ahead and modify those values in XFLR. Firstly, wing incidence, tilt angle, go to 2.88. Looks a lot more manageable, a lot more realistic now. And then you can also define the wing 0.49. Move a little bit. Okay, so now we have our wing position design defined, and then we also have our wing incidence is now changed. So now what we can do is if we go to heads, we can put in our plane mass and our CG location. And then I'm just going to delete this. I don't know why I made a second one. We can go ahead and run this. And then we can go ahead and run this as well. I'm just going to run them both back to back and just kind of see what that gives us. Very cool. So save this. So as you can see, negative slope, so it is statically stable. And then now we can look at our different modes. Mode 1 3 stable, and mode 3. Actually, that looks pretty good. If we bring that out over, say, 50 seconds. Yeah, that's pretty quick compared to what we had before, which is what I'm liking. So this is a lot more statically stable, or sorry, dynamically stable than what we had before. Kind of what we're looking at. So mode 1 and mode 3. So now our aircraft is finished refining, and so we can now move on to manufacturing.